MoNaCo here in our 6th lecture note video on kinetics. We're going to be talking about LeCheteliers' principle today. And LeCheteliers' principle is a principle that applies to only reversible reactions or equilibrium reactions. Remember, equilibriums are equal rates, a reaction that goes forward and then the reverse reaction also happens too. So LeCheteliers' principle is going to be talking about how we can manipulate those reactions to go backwards or forwards, to shift them in one direction, towards the product side or the reactant side. So let's get this full screen here. Alright, so we're going to identify how an equilibrium reaction responds to various different stresses. So the 6 things that you can do to speed up a reaction are pretty much the same 6 things that we're going to look at the stresses of, except it's going to shift the reaction in one direction or the other, towards the right, towards the left, that kind of thing. So how do we manipulate an equilibrium reaction to produce a desired outcome? If I want the equilibrium to shift to the right, what do I do? If I want it to shift to the left, what do I do? LeCheteliers' principle, he was a chemist, old guy, stated that equilibriums will shift to compensate for stresses put on them. We can make the reaction shift towards the product or reactant side by increasing concentration, heat, pressure, depending on which way we want the reaction to move. And we teach and do a lot of this going on. We're going to say A, T, T a lot when it comes to LeCheteliers' principle, because it's a nice mnemonic device to help us remember that we go away from whatever we add to the reaction, and we shift towards whatever we take from the reaction. So let's see what we're talking about in our notes. The LeCheteliers' principle at its most basic form explains how a system at equilibrium, so both forward and reaction happen at the same rate, will respond to stress. Well, everybody gets stressed out, but what type of stresses are we talking about in chemistry? Any change in temperature, concentration, or pressure put on a system at equilibrium. Notice we're not changing like the particle sizes or adding or taking away a catalyst, because those things have different effects that LeCheteliers' principle does not cover. So when a stress is added to a system at equilibrium, the system will shift in order to reduce that stress. So when you stress out one side of the reaction, it shifts to go to the other side of the reaction to get away from what you stressed out. So let's check out the next page here. A shift, increase in the amount, or the rate of either the forward or the reverse reaction. So a shift, you either go forward faster or reverse faster based upon what it is that you did to your reaction. A shift to the right, so towards products. It's a rate of the forward reaction increases or goes up. The forward arrow gets bigger. Okay? Reactants go to products faster. Products come to reactants a little bit slower. This favors the product side of the reaction. Okay? Now a shift to the left is basically the exact same thing but opposite. A rate of the reverse reaction increases so that backwards arrow gets bigger. Reactants are favored over the products. Bigger arrow coming backwards. It favors the reactant side. Okay? So that's what the shifts are. They're either going to be towards the reactants or towards the products. Different types of stresses. So these are the things that you can do to stress out an equilibrium. Concentration. Equilibrium changes when a reactant or product is added. So the equilibrium's been established, and if you add some more drops of reactant, it's going to push it towards the product side. If you add some more product, it's going to push it towards the reactant side. So when the concentration of reaction or product is increased, the reaction will shift away from the increase. So you increased means is added. So we've added something, and we shift away. That's why I'm going to keep telling you A. Away from what you add. Away from what you add in a LeCheteliers' equilibrium stress situation. Example 1. 4 moles of ammonia gas and 5 moles of oxygen gas are in equilibrium with 4 moles of nitrogen oxide gas and 6 moles of water, gas, and heat. Okay, so that's our equilibrium because we've got a double-headed arrow. So if we add H2O gas, the system would shift to the, let's see, so if we're adding H2O, we add H2O here, and we're going away from what we added. We shifted away from that, so we shift to the left. That's how AA works. Add, we shift away. So whatever you add, you shift away from. And the NH3 concentration, so if we shifted this to the left, the NH3 concentration would increase. Because if we shift the reaction to go more towards the left-hand side, there's going to be more of these things that show up. If we added O2, the equilibrium would shift to the, add O2, so away from what we add, it's going to shift to the right. And the NO concentration, if we're shifting towards the right, that means we're going to get more of these things. NO concentration would increase. Alrighty, and then let's see what's next. If we added H2O gas, the system would shift to the, let's see here. So we're going to add H2O gas, add this stuff again. We're going to shift away from what we added, so we shift to the left. And we have to answer the comprehension question, and the NO concentration would, well, NO is on the right-hand side. If we're shifting away from the right-hand side, that means all of these things, amounts of them are going to drop. So we're going to decrease the NO concentration. And if we added NO gas, which concentrations would decrease? NO gas, we're going to change this. NO gas, we add that. So we're going to shift away from what we added. What things would drop? So we're shifting towards the left, which means these things would go up, and these two things would drop. So the H2O gas and the heat amount would drop. So that's the concentration stress. When concentration of a reactant or product is decreased, the reaction will shift toward that has experienced a decrease in the concentration. So if you take something away, you shift the reaction towards it. So that's why we have the T. A, away from what you add, towards from what you take away. So let's see what we can get here. If we remove water in the system, it will shift to the, let's decide here. So we're going to start with water. If we're moving water, water's here, there, and we're shifting towards what you take away. So if I take away water, the reaction shifts more to the left, which means we're going to make more of these two things and take more of those two things. So we're going to shift to the left. And the C6H12O6, that's on the right-hand side, concentration would drop. So shifting to the left, everything on the right, concentrations go down. Decrease. AATT. If we remove O2, O2 is right here. It says if we remove O2, the system will shift to the, so towards what we take away. So we take away oxygen, we're going to shift towards it, and that's the right side of the reaction. And the C6H12O6 concentration is on the right side, so whatever we're shifting towards, we can make more of it. So we're going to get increased concentration of C6H12O6. I think it's a type of glucose. If we remove glucose, which concentrations will decrease? Well, glucose is C6H12O6, one form of it at least. If we remove this, we're shifting towards the right-hand side, which means that these concentrations increase, and these three concentrations decrease. So we'll be decreasing the kilojoules as energy. So we'll have less energy used, carbon dioxide used, and we'll have less water used. So everything on the opposite side drops. If we remove CO2, which concentrations would increase? Let's erase here. If we remove CO2, so CO2, so we take away CO2, remember we're going towards what we take, which means the reaction is going to shift to the left, and the things on the right drop concentration-wise, and things on the left rise concentration-wise. Remove CO2, which ones would increase? So we're shifting to the left, we're going to get more energy, CO2, and H2O. So AA, what you add, the system shifts away from. What you take, the system shifts towards. AATT. Temperature. So all you have to think about in this case is how temperature is one of the ingredients. And it is shown as heat, or kilojoules, or energy. Heat slash kilojoules slash energy. That's how you're going to see temperature in one of these particular reactions. So when temperature or heat is increased, the reaction will shift away from the reaction side containing heat. So away from what you add still. No change there. In the endothermic direction, just another layer of vocabulary there. So when temperature or heat is decreased, a shift will happen towards the side containing heat. So if you take away heat, you shift towards the side that has heat, or kilojoules, or energy. In the exothermic direction. Our examples, in this case, all we're doing is treating the heat as a product or a reactant now. That's energy, temperature. So let's check it out. If we added heat, which concentrations will decrease? So if we add more heat, we're shifting away from what we add, or towards what we take. So we're away from the heat side, which means we shift to the left. The concentrations here go up, the concentrations here go down. So we're decreasing NO and H2O concentrations. If we added heat, which concentrations will increase? So we still have added heat, don't have to erase anything there. And away from what we add is the shift that we go. So we're away from the right side, which means the left side's concentrations go up. So NH3 and O2 concentrations will rise. Example number 2. I want you to try this one on your own. And keep in mind, there is your heat or temp right here. So you're going to be adding or subtracting that. Remember, away from what you add towards what you take. Nothing different here. And as a result, you just remember that if we're shifting away, some concentrations rise, others will drop. Pressure. Pressure affects gases only. You can pressurize a solid and a liquid, but gas particles actually get closer together. Solids and liquids, that doesn't play the game. So it doesn't apply to collision theory, and therefore it doesn't apply to LeChatelier's principle. So gases only when we're talking about changing pressure. Again, away from what you add towards what you take. Reaction shifts to the least side with the least number of gas particles on it, or the least number of moles of gas. So you look and see who's got more gas on it, and it shifts away from it when you put more pressure in. If you decrease the pressure, it shifts towards the side that has more gas. Take away pressure, you shift towards the side that's got more gas molecules. Add pressure, you shift away from the side that has more gas molecules, pardon me. If the reaction contains no gases, or the reaction has the same number of gas molecules on each side, then there's no effect. So if whatever side you have more gas molecules on, has have a greater effect when you change the pressure. So if you increase the pressure, the side with more gas molecules shifts away from it. If you decrease the pressure, it shifts towards it. First example. We got carbon dioxide gas and carbon dioxide aqueous. If we increase the pressure, concentrations of which species will increase? Well, if we increase the pressure, the CO2 gas gets squeezed together more and reacts more, so it shifts to the right. So the concentration of CO2, AQ, would rise. You put pressure on a gas, it will dissolve in the water more efficiently. If we increase the pressure, the concentrations of which species will decrease? Well, by squeezing the gas more, it reacts and pushes the reaction to the right more, so the concentration of CO2 gas will drop, because we've squeezed more gas into the water in this case. If we decrease the pressure, the concentration of which species will increase? So we're taking away pressure, which means that we're going to shift towards the side that favors having more of a gas. If you reduce the pressure on a gas, it becomes more ideal, and the gas likes to play that ideal behavior. So if we decrease the pressure, concentrations of what species will increase? The CO2 gas. It's like when you pop the top on your soda can, you decrease the pressure inside the can, so all the gas comes from the aqueous state dissolved in your soda, and starts bubbling out and making the bubble gassy, fizzy in your soda pop. Okay? If we decrease the pressure, the concentration of which species will decrease. So if we remove the pressure, removing the pressure on the gas, it's like we're removing the gas, the concentration of the CO2 that's dissolved in the water is going to drop. So CO2, AQ, that's going to drop. So pressures is a little harder to think about when you're talking about LeChatelier's principle. Let's see here. Example 2. Again, ammonia. Making ammonia from nitrogen and hydrogen is called the Haber process. So what you've got here is when you change the number of the pressure, you're changing the gases on the left or the right. So you got to count the number of moles. The left side's got 4 moles of gas. The right-hand side's only got 2 moles of gas. So that's the situation that we've got here. Okay? So last slide here, identify which direction a reaction will shift in response to specific stresses. That is our main objective here. You've got some practice pages, quite a bit of this stuff. There's only one way to get it. Away from what you add, towards what you take. Poggle assignment on this, and some online quiz preps as well. Thanks for watching. Talk to you later.